Hello students, welcome back. Let us resume our discussion in section 6, Piecewise Defined Functions. We went through this example here. For Newton quotient for left-hand side, we have to use the first line. The Newton quotient for the right-hand side, we have to use the third line. Either way, f of 1 is explicitly given as 3, so that's what I can plug in. And then, please note that this function is continuous. And then the derivative computation, well, left-hand side and right-hand side, they're the same in this particular case, so the common value is the derivative. In some cases, they're different. In that case, the function is not differentiable. It has no derivative at x equals to x, this break-in point. Here's another example, but this time, let's find out a value so that this function is differentiable. So how am I going to do that? Let's take Newton quotient for the first line and the Newton quotient for the second line. Set them equal, then I'm going to get an equation with respect to a. Solve it. There you go. We're going to get the answer. So here we go. The Newton quotient for the left-hand side. And then let's calculate it using the first line. H is going to 0, a bit less than 0, so that's first line. H is going to 0, but a little bit greater than 0, so that's the second line. So first line, x is less than 2. And the first line, x is greater than 2. And it says function continuous. Please check. Plug in x equal to 2 and see if they are the same. If it is not continuous, then everything breaks down. Okay, let's calculate the first using the first line. Well, stop the playback and do it on your own. G of 2, what is g of 2? Plug in x equal to 2. 2 squared, so 4 plus 2a minus 2a. So this value is going to be just 4. So this value, g of 2, is going to be just 4. And then g of 2 plus h, well, that's what you have to plug in and do your computation. If you do, you're going to get this. This one here, left-hand side, that's going to be when h is already less than 0, so we're using the first line. X squared plus ax minus 2a, where x is 2 plus h. Break out the complete square and simplify, simplify, simplify. You're going to end up with 4 plus a. If you do the same thing with the second line here, and then simplify, 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 you're going to get a squared plus 2. A squared came from, of course, this a squared here, of course. These two have to be the same, so 4 plus a and a squared plus 2 must be the same. That's going to give me this equation. 4 plus h, the left-hand side, and a squared plus 2, the right-hand side, must be the same. So that's a quadratic equation. Solve it. We're going to get a equals to -1 or positive 2. It's an easy equation, so I'll leave those to you. So, we have a differentiable function at x equal to 2 if and only if f is -1 or a is -2. A is -1 or a is positive 2, excuse me. Otherwise, discontinuous. Excuse me. Otherwise, not differentiable. The derivative does not exist. They are cusps. They're all continuous, yes. By the way, this is a perfect solution, and this computation is perfect, but oh my, look at this computation. Can you follow that? Well, yes you can, given time, but oh come on. Let's consider a shortcut solution. Beware, it doesn't always work, but most of the time it does. Simply take the derivative of this and the derivative of that and then set them equal. So what's the derivative? 2x plus a. This is constant, so that's gone. Take the derivative, 2x, and then a is just constant, coefficient. And then here, take the derivative, a squared plus 2. Let's see, that's constant, that's gone. A squared is coefficient, derivative of x is just 1. Again, 2 is just coefficient, derivative of x is just 1. So that's what you're getting, a squared plus 2. Remember, this is constant, so that becomes 0, it's gone. That's constant, so it's gone. What's left is x squared, which becomes 2x, and then a times x, which becomes a times 1. Setting these two equal, what do you get? Plug in x equal to 2. 2 times 2, that's 4. So 4 plus a. And then here, nothing to plug in. X term is completely gone. So we have constantly a squared plus 2. And we have a quadratic equation. Solve it. We have the same answer. Same equation, same answer as before. Let's compare. Newton quotient computation, left-hand side, right-hand side, versus shortcut derivative computation. First line, second line, and set them equal. Once you set them equal, we get the same equation, same solution. You see? This one up here, and down there, they're the same. No problem there. The difference between the derivative computations and the Newton quotient computations, the difference is like night and day. So perfect solution is great. It always works. But in practice, the shortcut solution will work pretty well, especially in an exam environment. Take the derivative of the first line, take the derivative of the second line, and then set them equal. Please check the continuity of the original problem if you have time. If they are not continuous, then everything breaks down. By the way, here's a visualization. So, for different a values, apparently we don't have differentiability here. Ooh, what's going on there? Let's see. The solutions are what? -1 or 2. Okay, alright. Let's stop there. X equals to -1. Okay, right here, right here. In this case, we have differentiability. Let's see. This tangent line and that tangent line, they match. And +2. Again, they match. Tangent line here, then that tangent line is itself. Otherwise, we have the vertex forming. Yeah, cusp forming. Okay, kind of like continuity condition, you can set up an equation to solve it. Let's see, what about the next problem here? Find a value. Okay, pretty much the same, but this time we have a trigonometric function. So let's postpone this. Maybe next time. Now, how about this one? Continuity and the differentiability put together. Oh boy, this is going to be a challenge. Find a condition for which the given function is continuous. So plug in x equal to -2 to the first line, plug in x equal to -2 to the second line, set them equal to each other, and find out appropriate a and b values. Set them equal, we're going to get an equation, but we have two possible unknown variables, a and b. How am I going to get it right? Well, if you do it right, one of those will just disappear, and we can determine either a or b. Stop the playback and try. It's not hard. So what did you get? Plug in x equal to -2 and set them equal to each other. The first line and the second line, and set them equal to each other. -2a cancel each other out, and we have an equation of just one variable b, so b is -2. So b equals to -2 will give me the continuity. So plug in b equals to -2 back into this equation, back into this problem. B is -2. So b is -2, so that's +6. B is -2, so that's +2. Okay, all right, we have a new problem. And then we can do something similar and find out a value. Let's go back to the previous problem. You see, the first line blue and the second line red. When x is less than -2, greater than or equals to -2, let's see. This one here uses the first line, and this one here, the second line, and the function value is going to be one of those two, so it doesn't really matter. You have to set each other equal to each other, so blue equals to red, and then -2a drop out, and we ended up with b equals to -2. So we got halfway through, b value we found out, and then plug in that b value, we have a new problem. And then calculate the Newton quotient or shortcut. Yes, we have a continuity, so the shortcut will work. Let's see, what do you have? Just a shortcut, all right. Take the derivative here, and take the derivative there, and set these two equal. Wait a minute, b value is -2, so that's +4. +4 times -2, so that's -8. So -5. Okay, I plugged in b equals to -2 way too late. I could have done it earlier, which I did. Then the problem would have been simpler. In any case, if I do that, I get a value as well. A is -5. You can do the same thing with Newton quotient, like this, and then also like that, and then work out. Good luck. Either way, you're going to get the same value. Do you have enough time for a visualization? Well, let's see. So, changing b value, we get discontinuity, and then at b equals to -2 precisely, we have continuity. Now fix this, and then change a value. We do not lose discontinuity because b is now fixed as -2. And then, when a value is -5, that's when we have the differentiability. Yes, we have the tangency.